This is Miss Louise with East Central High School in San Antonio, Texas. So this year in my AP Calculus BC class, we're going to be using a flipped classroom model. So your first video should have been already watched for homework the other night, and it should have explained what the expectations are in a flipped classroom and what a flipped classroom is. So every video will start off with a screen that looks very similar to this, very much like the one we use in class. Things you want to always get in your journal. Okay, everybody has a table of contents in their journal. First thing you want to do is write down the actual lesson in your table of contents. That lesson will correspond with a page number, so that it's our page number 1. And all of your notes that I give you will be in they will be numbered numerical order, and they're going to follow along what you see on the screen. Okay. Last thing that you should really recognize is, in fact, the standard that we are dealing with. So this is standard L1. So you want to get those 3 things in your journal. Okay. Table of contents is going to be pretty important. Okay, so the goal behind this lesson, or the target behind this lesson, it says students will calculate the limit of a function algebraically and graphically to identify the characteristics of a function as a certain x value is approached. Okay, so the idea of a limit, if you're in pre-cal, you may have already touched on what a limit was, so this may be a little bit of a review. If you did not, this is going to be brand new. Just kind of go along and write down any questions that you may have. So those are things that we can address first thing in class on the next day that I see you. Okay, so we're just going to dive into what a limit is. Okay, so if we think about the graph, if we think about a specific function, like the function that I have here, x cubed minus 1 over x minus 1, where x does not equal 1. Okay. The idea of this rational function, so in Algebra 2 and in pre-cal, you talked about rational functions and about how rational functions have certain types of discontinuities because of the idea that if we plugged in that 1 there, we'd get a 0 in our denominator. And we know we can't be dividing by 0. We don't ever want to do that. That's not a mathematically accurate thing to do, or just can't be done. You can't divide something into nothing. But the idea of we don't care about what the function truly is. We care about what our function is approaching, this idea of approaching something. Okay, so if we look at our graph, the ultimate question we want to ask is really, what is f of x approaching as x approaches 1? So if you put your fingers on the graph, so let's say put a finger here, put a finger here. And what I want you to do is to move those fingers towards that removable discontinuity. And I'm going to draw on a line there. So we're going to move our fingers towards that line. Okay. And what we're going to do is we're going to look at what's happening as we get closer and closer to that value of x equals 1. Now, because of the fact that our fingers, if you did it, came together on both sides, we would say that what we're doing is we're approaching 3. Okay, we know the function's never going to be equal to 3, but it is approaching this value of 3. So as we get closer and closer to 1, 0.9999 or 1.0001, that value that's produced is going to be a number that's really, really, really close to 3. Okay, we're going to kind of prove that in a minute. Okay, so if we think about what's happening, we can write this symbolically using mathematics. And the mathematical language is important. The way we write mathematics and communicate mathematics is really, really important. So that's going to be something we focus on this year. Okay, but if I was to write the idea of approaching, that's what a limit is all about. It's about what is our y value approaching as we approach a very, very specific x value. Okay, so it's about the approach, not the value. Another way you can think about it is a limit is about the journey and not the destination. I know that's a little corny, but you'll get used to it. But we can write this as a mathematical statement symbolically, and it kind of looks like this. And we talked about how to read these. So we're talking about the idea of a limit. So we use LIM for limit of the function, and we can either write f of x because it does have a name, or we can write the function here, and I'm just going to write the function. So the limit of x cubed minus 1 over x minus 1 as x approaches 1 is equal to 3. Okay, so the limit of x cubed minus 1 over x minus 1 as x approaches 1 is equal to 3. The function is not equal to 3. The limit is equal to 3. So that's going to be really, really important because the function is undefined. We know that. Okay. If we look at a table, and this is kind of what I was talking about earlier. If we look at a table, okay, so I have this table here. My table looks a little bit different than yours, but what I want you to do is to write down these values next to the correct corresponding x value. Okay. If we look at this approach, now when we approach a limit, we approach limit from both directions. From what we consider to be the left side or the negative side, okay, of the value, and the right side, or what we consider to be the positive side. What we want to do is look at these values that we put in here and see if they're approaching or getting close to some x value, or I'm sorry, some y value on both sides. So really what we want to look at is probably the ones that are closest to this. We want a couple of values to see if there's a pattern. That's important. But in the end, we want to look at the ones that are closest. And if those two numbers are about the same value, we would say that the limit is approaching that value. So 2.997, 3.003, very close to 3, which is why we say the limit is in fact 3, because it's approaching 3. If we got closer, it would be even closer. So kind of the formal notation, or the formal way to write it, is the limit of f of x as x approaches a certain value, in our case 1 in our problem, equals a number, in our case 3. So kind of the way I said earlier, but an informal way to think about it is really what's happening to our y value as we get closer and closer to a specific x value. That's really the question. What's happening? We just want to know what's going on. Okay. So underneath this, you have two more tables. My tables are already filled out. So what I want you to do is to pause the video and fill out those tables. Okay, fill out the y values. And then when you're ready, press play again. So the first limit is 1 over x squared minus 1 as x approaches 1. So what we want to look at is this value of 1. Okay, that's what we're interested in. What's happening as we get closer? We know it's undefined at 1. Okay, but we want to see what's happening as we get closer and closer to this value. So we look at it from two sides. Like I said earlier, the negative side, that's the left side. And we want to see what's happening. What are these values getting really, really close to? So we have -5, -50, and then -500. If we put 0.9999, we would probably get -5,000. So those numbers seem to be growing larger and larger and larger the closer we get. If we think about the idea of the largest number possible, we represent that with, of course, negative infinity, because these are negative values. So we would say that this is approaching negative infinity. Okay. If we look at it from the opposite side, let me get a different color. If we look at it from the positive side here, and the approach, it's kind of doing the same thing, but in the positive sense. So we would say that it's approaching positive infinity. Okay. Now, the limit is equal to a numerical value. Infinity is not a numerical value. So in this case, we would say that the limit, in fact, does not exist, or DNE for short. Okay. We could even say that this limit is infinite, okay, using the infinity symbol. Okay, some might argue with that because one side is negative, one side is positive. But we can also say that this is an unbounded, well, we don't want to say equals, but it is an unbounded graph. Okay, if we think about this function. If we think about the graph of this function, okay, at 1, there's actually a vertical asymptote. And the graph from the right side approaches positive infinity. So it's going to go like that. You guys are used to seeing these graphs. And on the negative side, negative infinity. So our graph looks like that. So it's unbounded. It's going to grow faster and faster and larger the closer we get. If we think about the next one, the idea of approaching, again, 1. The next one is a little weird because it is a absolute value. Okay, so we're still approaching 1. At 1, still undefined. But if we look at it from the negative side, and we approach that value, every single one of those values is -1. So from the left side, it's approaching -1. Makes sense. From the positive side, though, so this is our positive side, as we approach, this side's approaching +1. Because those two are not equal to each other, the left side and the right side do not agree, we would say that this limit does not exist. And the reason that's happening is because of the fact that there's a jump discontinuity there. If we look at the graph, this graph from the left side, let's say that this is 1, that's 1, and from the positive side, it looks like that. So as we approach, there's kind of a jump discontinuity in between it, therefore our left and our right do not agree, therefore the limit would not exist. Left and right have to be equal for the limit to exist. Now, I've been talking about this idea from the left, from the right. We also have what we call one-sided limits. I don't need a keyboard. I need the picture. Okay, one-sided limits. Okay, and the way we notate one-sided limits is kind of different from what you've seen right now. We use a notation that looks like this. And what's happening is we put a symbol behind the number. So there's a plus or a minus. If there's a plus, what that means is we're approaching from the right. So we're approaching. Of 1. Okay, because 1 is the value. It's not a positive one, but it's just we're approaching that number from the right. Okay, so I tend to use highlighters, especially if we're not used to looking at limits. Kind of gives us a focus. So I'm going to put a vertical line at 1. In fact, the line x equals 1. And if we approach it from the right, that means we're approaching from this side. This side is the positive side, the right side. If we approach from the right alone, we would see that our y value is getting really, really close to 2. So we would say that this limit is equal to 2. If there's a negative sign, that doesn't mean -1 if the negative is behind it. That means we're approaching from the left. Okay, so on this side, the left of that line is this side of the graph. We have to be on a graph to approach. So as we get closer and closer, our y value is approaching 1. I'm not saying the y value is 1, I'm saying it's approaching 1. And those two things mean two different things in the world of mathematics. So this idea of LIM, this limit, it's an operation. It's what we're doing, it's what we're trying to get close to. Just like a plus sign when we add, just like a division sign when we're dividing. It's kind of an operation symbol for us. Okay? It's telling us what to do. Okay. So on the next graph, I'm going to do one column, and then you guys are going to do the last column. So if we look at the next graph, okay, I'm going to do the first column. So if I look at those limits, they're all looking at 2. So 2's right here. Again, I'm going to use a highlighter here. Okay, and what I'm trying to do is I'm going to try and approach that highlighted line right there. So the first one says approaching f of x from x as x approaches 2 from the negative side. So our negative side of this line is this piece right here. Sorry, I need a pin. This piece right here. So I'm approaching that line from the negative side. And that value is like 1, 2, 3, 4. Let's assume that they go by ones. Okay, 4. If I approach from the positive side, I'm approaching that same value, which is 4. If our left and our right are equal, that automatically means when we approach 2 from both sides, also equal to 4. Okay, remember this is about what our function is approaching, not what our function is. And at 2, if we look at that point right there, that's an open point. So that point does not really exist. In fact, the function exists down here at that solid point. So now on D, since we're talking about the function, that's -2. We're not looking at -2, we're looking at +2. So -2 is right here, that closed point. Okay. I just have these all mixed up. So let's pretend that that's a positive. Okay, that's a +2. Okay. So really we're looking at that point right there. Sorry about that. I would say that this would be my last mistake, but that's probably not true. Okay, so as we approach 2, that's +2, our y value, our function, is actually equal to -1. Okay, so our function and our limit, those are two separate things. Limit is about the approach, function is about the exact. Sometimes they are the same, sometimes they're not. Okay, so what I want you to do is pause the video, do E, F, G, and H, and then come back and see if you got them right. And I'm going to work them out. Okay, so once you're done, press play. So if we look at E, now we're looking at -2, which is right here. Okay. If we're approaching from the negative side, so here's my negative side of that line. So as I'm approaching here, my y value is approaching 2. So if you got that right, good job. From the positive side of that line is on this side now. As I'm approaching from this side, I'm approaching 0. If you got that right, good job. So the -2 without symbol means I'm approaching from both sides. Because these two are not equal, that means that this limit does not exist. And the reason because is there is a jump discontinuity. Okay, and then the last one, f of 5, that's over here, and that's 0. So hopefully you got that. Okay, so there's 3 reasons for a limit to fail to exist. We've experienced 2 of them. Okay, the first one, of course, is a jump discontinuity. That's terrible writing, sorry. Okay, and what that means is the limit as x approaches a certain value from the positive side of a function, and the limit as x approaches some value from the negative side on that same function. Those 2 things do not exist. Okay, so that proves a jump discontinuity for us. The second one is, we say an infinite. Okay, behavior. Okay, we could say it's unbounded. And what that means is our limit as x approaches that value is equal either to positive or negative infinity. Okay, because it's getting larger and larger, it's unbounded. Okay, and then the last one here is what we call an oscillation. Oscillation. Okay, and an oscillation happens if we're looking at a specific value. The function is bouncing up and down too fast, and it's going between positive and negative, or it's going between 2 values, and we can't really decide what value that occurs on. A lot of times with these types of functions, you're dealing with some type of trig function. So tomorrow in class, I'm going to introduce to you one that actually does that. It's a rare type of limit failing to exist, but it does happen. Okay, so any questions you have, come in tomorrow, and then we'll do some work with limits.